Mixture of gases, sample problem number 1. So for sample problem number 1, we are given with a mixture of fuel composed of 68% methane in volume and 32% ethane in volume. So we need to write the balanced combustion equation if there is 100% theoretical air and if there is 20% exist air. So our solution for the first requirement, 100% theoretical air, can be based on case number 1. So 100% theoretical air is case number 1, excess air case number 2, and efficient air case number 3. So since this is 100% theoretical air, we will use our equation for case number 1. But this time we have two fuels. We have methane and ethane. So in order for us to solve the value of M and N, so we need to solve for the total M and N atoms, the total carbon and hydrogen atoms for the fuel. Since we have a mixture of two fuels, so we will add the number of atoms of carbon and hydrogen based on their percentage volume composition. So for M, which is the number of carbon atoms, so we add 68% or 0.68 of one carbon atom from methane. So we add one carbon atom plus two carbon atom with 32% volumetric composition for ethane. So solving this, that's why we have 1.32 carbon atoms. For the number of hydrogen atoms, so we add 68% of 4 hydrogen atom and then 32% of 6 hydrogen atom in ethane. That's why we have 4.64 total hydrogen atoms. So this is our collective number of hydrogen and carbon atoms. So we will substitute this to our equation for 100% theoretical air, which is case 1. So substituting, so we have, so this one, since this is 68% in volumetric composition, in number of moles, that is 0.68 mole. So 0.68 mole of methane plus 0.32 mole of ethane. So this represents the fuel plus the air. So we have M plus N over 4, so that is 1.32 plus M over 4 O2 plus 3.76 M plus N over 4 N2, and then this represents the air, and then we have the products of combustion, carbon dioxide, M, CO2, then we have N over 2 H2O plus 3.76 M plus N over 4 N2. So simplifying, solving for the values of number of moles, that's why we have this. This is our balance equation for 100% theoretical air. So the other requirement is for us to find the equation when there is 20% excess air. So for 20% excess air, this is also the same as 120% theoretical air. So we will use case number 2 since this is excess air. So our equation for case number 2 is given as this equation. So in this equation, we don't have the value of Y and then YCC, or the chemically correct number of moles of this hydrogen atom, oxygen atom. So we solve for YCC from the result of 100%, which is case 1. So YCC, or the chemically correct number of mole, is available in the first equation, and that is the formula M plus N over 4. So substituting the value of M plus N over 4, our YCC is 2.48. So the only unknown left is your Y. So we have a relationship between Y and YCC in this form. So from that, we can solve for the value of Y since E is given. This is the excess air. So the excess air is 20% or 0.2. So substituting the value of YCC, we can solve for Y. So Y is 2.976. So we substitute Y and YCC to our case 2 equation, as well as the value of M and N. So that's why we have this. And then simplify so that we can have our equation for 20% excess air or 120% theoretical air. So this one represents the equation for 120% theoretical air. So this time, there is a presence of oxygen in the products, unlike the 100% theoretical air.